Car Evaluation Classification, an end-to-end hands-on lesson. We will solve a car evaluation problem using real categorical data. This task is important because it shows how to automate decisions about car acceptability. You will learn how to pre-process, analyze, and build machine learning models for a fully categorical dataset. We will cover data exploration, pre-processing, modeling, and debugging techniques. By the end, you will be able to classify car acceptability using accessible Python tools. Running the cell now. Before we explore the dataset, let us make sure we import all the necessary libraries. Each library helps us manage, analyze, or visualize the data or results. We import NumPy for numerical operations. We import pandas for data manipulation and handling tabular data. We import train_test_split to split our data into training and testing sets. We import OrdinalEncoder and LabelEncoder to convert categorical values into numbers. We import classification_report and confusion_matrix to measure model performance. We import DecisionTree classifier and export_graphies to build and visualize decision trees. We import matplotlib.pyplot to plot graphs. We import Seaborn for fancy data visualizations. We disable warnings so the notebook is cleaner for learning. We set C to 42 for reproducibility so our results stay the same if run again. Running the cell now. Try running just the first 4 import lines and see if they work for you. If not, install the missing libraries. Subscribe to our channel for more deeply practical data science lessons. Understanding the car evaluation dataset. The car dataset contains 1728 entries and 6 features, all categorical. Each feature represents a property of the car, like buying price or safety level. The target variable, class, tells if a car is unacceptable, acceptable, good, or very good. There are no missing values and all features are non-numeric. Beginners often forget to encode categorical variables, which causes errors. Running the cell now. Let us load the car evaluation dataset directly from OpenML so we can start working with the real data. We fetch the car dataset with OpenML. We load the data as a pandas data frame called car_df. We print the shape to see how many rows and columns there are. We display the column names. We view the first 5 rows of the dataset. Running the cell now. This output confirms the car evaluation dataset has 1728 rows and 7 columns, including the target class. Notice all features, like buying price and safety, are categorical and non-numeric, consistent with the dataset description. This initial inspection ensures we understand the data structure before proceeding with analysis or modeling. Check the column names and make sure they match your expectations. Let us quickly look at the distributions of values and check if data is missing. We use describe to get a summary of all columns. This will show us unique values, most frequent value, and counts for each feature. We print the number of missing values for all columns to confirm the data is complete. Running the cell now. This output confirms the car dataset has 1728 entries and no missing values across all 6 categorical features plus the target class. Notice the categorical nature reflected in unique counts per column and the most frequent categories, like hide buying price and UNACT class, highlighting the dataset's distribution and preparing us to handle these non-numeric values in modeling. What is the most common class label? Try to spot it from the output. Beginner example 1, value counts. It is important to know how many times each target class appears. Imbalanced data can make some models unreliable. Let us check the target distribution. Running the cell now. Let us count each class, then visualize the class distribution. We print the value counts for the class column. We use Seaborn to plot the distribution of car classes. We give a title to the plot for clarity. We label the x-axis as count. We label the y-axis with car class. We display the plot. Running the cell now. The output shows the number of occurrences for each car class, revealing a clear imbalance. UNAC dominates with 1210 entries, while the VGOD is the rarest at 65. This distribution, also visible in the bar chart, highlights why it's crucial to recognize such imbalances early, as they can affect model performance and fairness. Understanding these counts helps us prepare for handling or correcting class imbalances in later modeling steps. Does it look balanced? How might this affect learning? Think about it. Beginner example 2, checking categorical variables. All features are objects, also known as categorical data. We should confirm the unique values for each feature. This helps avoid later mistakes during pre-processing. Running the cell now. Let us print the unique values for every feature. For each column in the dataset, we print its name and all unique values. This shows the allowed categories for each feature. Running the cell now. This output shows the unique categories for each categorical feature in the dataset, confirming that all features contain a manageable number of distinct values. Notice inconsistent categories like VI, high, med, and LOS helps us verify data quality and prepares us to properly encode these variables during pre-processing. This step is crucial to avoid errors later in the pipeline by ensuring we fully understand the categorical values present. How many unique values does safeties have? Check the output and discuss with a friend. Beginner example 3, encoding categorical features. Machine learning models need numbers, not strings. We must convert categorical data to numbers. OrdinalEncoder turns category strings into integer codes. Running the cell now. Let us encode the input features so a machine can learn from them. We drop the target column so X is features only. We copy the target column into Y. We create an OrdinalEncoder to convert categories to numbers. We fit and transform X, turning all categories into encoded numbers. We print the first 5 encoded rows. Running the cell now. Here we see the first 5 rows of our dataset after applying OrdinalEncoder, which has transformed all categorical columns into integer codes. Notice how each original string feature is now represented by numbers, enabling models to process this data numerically. This encoding step is crucial for preparing categorical variables before training a machine learning model. Which column is being encoded as 0 for its first value? Compare with the earlier unique values. We also need to encode the target classes for our model. We create a LabelEncoder for the target variable. We transform Y into integer labels. We print the unique encoded labels. We show which numbers map to which class names. Running the cell now. Here, the code uses LabelEncoder to convert categorical class labels into numeric codes that a machine learning model can use. Notice that the original string labels like RACCs and a VGOD are mapped to integers 0 through 3, which correspond to the unique categories in the target variable. This confirms how encoding preserves category identity while making the data model ready. Try switching label_encoder.classes_order. What might happen if it changed? Now we split the data into training and testing so we can build and evaluate our first model. We use train_test_split to divide the feature data and target labels into training and testing sets. We reserve 25% of the data for testing. We print the shape of the training feature set to see how many samples and features it has. We print the shape of the testing feature set to see how many samples and features it has. Running the cell now. Here we see the result of splitting the encoded dataset into training and test sets. Notice that the training set contains 1,296 samples and the test set 432, both with 6 features, matching the columns after encoding. This confirms that our data is properly prepared and ready for model training and evaluation. Why do we stratify? Try it without stratify and compare the class balance. Intermediate Example 1, Training a Decision Tree. Decision trees work well with categorical data. Let us fit a tree classifier to the training data. Running the cell now. Let us instantiate and train the tree classifier now. We create a decision tree classifier and set random_state for reproducibility. We fit the tree to the training data. We confirm the training is finished. Running the cell now. This output confirms that the decision tree classifier has been successfully trained on the categorical training data. It signals that the model is now ready for evaluation or prediction, highlighting the code's intent to fit a decision tree with a control depth for better performance and interpretability. Change max_depth and see if the training accuracy changes. Let us evaluate our model and interpret the results. We use the train tree to predict classes for the test set. We use scikit-learn's classification_report to print precision, recall, and F1 score for each true class label. Running the cell now. This classification report summarizes the decision tree's performance on the test set, showing key metrics like precision, recall, and F1 score for each class. Notice the high recall for VGood, 1.00, but very low precision and recall for good, indicating the model struggles to correctly identify that class. Overall, the weighted averages reflect decent accuracy, 0.87, highlighting the tree's varying effectiveness across categories, which is typical when handling categorical data of different frequencies. How well does the model perform on a VGood and good? Why might that be? The confusion matrix will help us see which classes are confused with each other. We calculate the confusion matrix based on test predictions. We visualize the confusion matrix as a heat map with tick labels for class names. We label the y-axis as true label. We label the x-axis as predicted label. We add a title and show the plot. We add a title and show the plot. Running the cell now. This confusion matrix visualizes the performance of our decision tree classifier on test data, showing counts of true versus predicted labels. Notice the diagonal values represent correct predictions, highlighting how well the tree handles each category. This confirms the model's effectiveness in classifying categorical data, aligning with our goal of training a decision tree. Spot the biggest confusion. What mistake could this mean on the business side? Intermediate Example 2, Cross-validation. Cross-validation lets us test model stability on different data splits. We will use cross_val_score to get accuracy scores across 5 folds. Running the cell now. Now we check if our model's performance is consistent, not just lucky for one split. We import cross_val_score from scikit-learn. We run the classifier over 5 folds to get several accuracy values. We print the accuracy scores for each fold. We also print the mean accuracy across all folds. Running the cell now. The cross-validated scores show accuracy values for each of the 5 different data splits, ranging roughly from 0.63 to 0.83, highlighting some variability but overall strong performance. The mean accuracy of about 0.76 summarizes this stability across folds, demonstrating how cross-validation helps us reliably estimate the model's generalization ability beyond a single train test split. Try changing CV to 7 or 10 and see what happens to mean accuracy. Intermediate Example 3, Feature Importance. Some features have more influence on the decision than others. Feature importances help prioritize certain car attributes over others. Running the cell now. Let us see which car attributes matter most in decision making. We get the feature_importances_ from our decision tree. We assign the correct feature names for clarity. We create a data frame to organize the importances. We sort the feature importances from highest to lowest. We print the importance table. We plot a bar chart of importance scores. We display the plot. Running the cell now. This output shows the relative importance of each feature in the decision tree model for car evaluation, with safety being the most influential and doors having no impact. Notice how feature importance values guide us to focus on key attributes like safety and persons when making predictions. This aligns with the lesson's goal of using feature importance to prioritize which car attributes matter most in the decision process. Which feature is most important? Why might that make sense? Advanced Example 1. Exporting and visualizing the decision tree. Visualizing models helps understand logic behind decisions. Let us export and view the tree as a .dot file. Running the cell now. Now we save a visual representation of the tree for further exploration. We export the trained decision tree as a .dot file, which contains instructions for visualizing the model with feature and class names highlighted. Running the cell now. Opening the .dot file generated by export_graphies so you can visualize the tree using external tools. Try opening car_tree in an online viewer or use graphies on your computer. Let us try to display the decision tree inline if graphies is available in your notebook. We import the graphies library. We read the content of the .dot file we saved earlier. We create a visualization source object from the .dot code. We display the decision tree if the environment supports it. Running the cell now. The error module not found error, no module named graphies indicates that the graphies Python package required to render and visualize the decision tree is not installed in your environment. This highlights the importance of setting up all dependencies before exporting and viewing model visualizations, as missing modules will prevent you from seeing the tree structure and understanding the decision logic. Be sure to install graphies with pip install graphies to proceed with this advanced visualization step. Does the structure match your expectations about the most important feature from earlier? Advanced Example 2. Trying another classifier, RandomForest. Decision trees can be unstable, so RandomForest averages many trees. RandomForest can give better accuracy for classification. Running the cell now. Let us see if RandomForest does better than a single decision tree. We import RandomForest classifier from scikit-learn. We create a forest of 100 trees, limiting max depth to 8. We train the RandomForest on the training data. We use the trained model to predict the test set classes. We print a classification report with precision, recall, and F1 for each class. Running the cell now. The classification report shows that the RandomForest model achieves high overall accuracy of 94%, effectively handling the largest classes like ViewNAC with near-perfect precision and recall. However, notice the good E class has high precision but low recall, indicating the model is conservative in predicting it but often misses these cases. This highlights how RandomForest balances multiple trees to boost stability and accuracy across uneven class distributions. Is the performance better than before? Try adjusting n_estimators and note the effect. Advanced Example 3. Hyperparameter tuning, grid search. Models often improve with tuning different parameters. We will use GridSearchCV to search for the best hyperparameters. Running the cell now. Let us optimize our tree model by systematically searching for the best parameters. We import GridSearchCV for hyperparameter search. We define a dictionary named param_grid listing values for max_depth and minute_samples_split to try. This line specifies the values for max_depth as 4, 6, and 8. This line specifies the values for minute_samples_split as 2, 5, and 10. We create a GridSearchCV object using a decision tree classifier with random_state42 and threefold cross-validation, passing the parameter grid. We fit the grid search object on the training data to find the best parameter combination. We print the best hyperparameters found by the grid search. We print the best cross-validation score obtained during the search. We assign the best estimator found to the variable best_model for further use. Running the cell now. This output shows the best combination of hyperparameters found by GridSearchCV, with a max_depth of 8 and minute_samples_split of 2, which achieved the highest cross-validated accuracy of about 91.9%. Notice how the tuning process systematically explored the parameter grid to improve model performance beyond default settings, illustrating the power of hyperparameter optimization in building more accurate decision trees. Try modifying param_grid, add or remove max_depth values and see if your score improves. How much predictive accuracy did we gain by tuning parameters? We use our best found model to make predictions on the test set. We print a new classification report to see if performance improved. Running the cell now. This classification report shows how our best model, found via GridSearchCV, performs on each class, highlighting precision, recall, and F1 score along with support counts. Notice that while accuracy is high at 95%, the Goody class has lower recall, 0.59, indicating some missed predictions despite perfect precision. This output confirms the value of hyperparameter tuning by improving overall metrics, but also points out areas to focus on for further model refinement. Even if results are similar, notice any differences for smaller class labels. Error handling example 1, using the wrong encoder. A common bug is to encode target with OrdinalEncoder, meant for features. This can cause errors or hidden issues in training. Running the cell now. Let us simulate an encoding mistake and see what the output or error is. We start a try block to attempt encoding the target variable. We apply OrdinalEncoder to transform y into integers, reshaping y to a 2D array. We print the unique values of the encoded target to verify the encoding. If an exception occurs during encoding, we catch it here. We print out the error message describing what went wrong. Running the cell now. Here we see that using OrdinalEncoder on the target y does not raise an error and produces encoded labels a 0, 1, 2, 3. However, this is a hidden issue because OrdinalEncoder is designed for features, not targets, and may lead to unintended consequences during model training. The key takeaway is that even when no error occurs, using the wrong encoder can corrupt the target data. Can you explain why LabelEncoder is the better tool here? Error handling example 2, missing value simulation. Sometimes missing values sneak into the dataset by mistake. Let us create a missing value and observe what happens if we run encoding or modeling. Running the cell now. Let us force a missing value and see the encoder's response. We copy the feature data into x_missing. We introduce a missing value in the top left cell of x_missing. We start a try block to attempt encoding. We create an OrdinalEncoder instance named encoder_missing. We try to fit and transform x_missing with the encoder. We catch exceptions as variable e if encoding fails. We print the error message explaining why encoding failed. Running the cell now. How does scikit-learn suggest you handle missing values? Best practices and patterns. Always check categories and target label balance before modeling. Always encode categorical variables before fitting a model. Use stratified splitting to maintain target class balance. Set random seeds for reproducibility. Try multiple algorithms, not just one. Tune hyperparameters for better results. Always use proper error handling for unexpected data. Running the cell now. Tiny end-to-end pipeline, raw data to prediction. Now we will go from loading the raw data to making one final prediction. We will bundle all key steps in one code cell. Running the cell now. Here is a single cell for loading, pre-processing, training, and testing the car evaluation problem. We load the car dataset from OpenML directly. We separate input features and target class. We encode input features to numbers with OrdinalEncoder. We label encode the target for model compatibility. We split the dataset into training and test parts using stratified split. We create a decision tree classifier and set the depth limit. We train the model on the training data. We use the trained model to predict test set labels. We print a classification report to evaluate the result. Running the cell now. This classification report summarizes the model's performance on the test set after loading, encoding, splitting, training, and predicting all within one pipeline. Notice the overall accuracy of 88%, but also that class 1 has 0 precision and recall despite being a smaller subset, highlighting potential class imbalance or difficulty in predicting that class. This output demonstrates how the entire end-to-end pipeline can quickly reveal strengths and weaknesses in model predictions across all classes. Try changing the model used here, e.g., use RandomForest classifier, as a practice assignment. Give this video a thumbs up if you like quick end-to-end solutions. Recap and further practice. We classified car acceptability using a fully categorical dataset. We covered pre-processing, modeling, evaluation, error handling, and best practices. Experiment with more algorithms and parameters for deeper learning. Practice by tweaking the pipeline and reporting new results. Subscribe and share if you found this hands-on session useful. Running the cell now.